So last time we did the law of large numbers and the central limit theorem. So the law of large number had concerned numerical variables, and so let x be a random variable. So it will have a mean, and denote mu its mean. So usually what you want to compute is the mean. I mean, one of the possibilities is to compute quantities, is to compute this object x, and mu is the mean, its mean, and is one of the objects you may want to compute. But you cannot usually, you can only take samples in statistics. So let x1, xn be independent samples from x, and we can compute the sample mean, so which is this object here. Is simply the mean of the numbers you collect. And the law of large numbers was told us that this mean, which is a random number, if n is big, it will be a good approximation of this, the real mean of the distribution that you want to compute. So, for instance, this x can be like, I don't know, the whole population of the citizens of Moscow. We did this example. Mu, the mean of the heights. So the example was this one. So we put in the vector heights like some random numbers. So let's say that the whole population is 1 million. And we have this vector heights, which will have a mean which is usually unknown to us, and is 180. So now, assume we want to compute this mean, the mean height of citizens. What do? Is to take a sample from this vector. So we take some people at random, and we measure them. So we take the sample size, which is much smaller than the all population size. So let's say 1,000, and we sample from this vector some heights, and we can compute the mean. And it will be a good approximation of this number, 180. Okay. So you see, it is really similar. So this was the object of the law of large numbers, and as a consequence, to know the distribution to know the distribution of a random variable, we can plot the histogram of the samples. So we take of a large sample. So, so let's see, this was a consequence. So let's use this fact to see what is the distribution of the sample means. So basically, we have to do the above code to replicate the above code k times. So, we want to have like k sample means. So let's take 10,000 of them. So this is the number of times we sample the mean. So let's replicate the above code. So many sample means will be like will collect all the results of the above code replicates many times, so k times. So we take the mean of I don't know, we sample from a distribution. So we sample in this case from the vector heights. How many times? What is the sample size? Let's take a small sample size. So let's take a sample size of 10. So do you know? Have you following this code? So we take a sample size. We take 10 people, we measure them, and we collect the mean. Then we do it again k times, simply to plot this mean and see how this mean distributes. So let's plot this many sample means on a histogram to see how they distribute. So the aesthetics here is only on the x-axis we plot this x, and let's also fix the endpoints of the plot so that we will see this mean, this distribution concentrate on the real mean. So let's see what happens. So xlim will be around 175 and 185, since we know that it will concentrate around 180, this distribution. So let's see the plot of let's see the law of large numbers in action. Um, so why is taking so much time? It's not really a big number. We replicate 100, no, 10,000 times a sample, so shouldn't take so long. Let's decrease this k here. And let's run again the code. Okay, so you see that the distribution distributes around 180, and this is like the law of large numbers, but you can have with some fraction, I mean, with some probability, you can also have values that differs from like 2.5 centimeters from the real height. So, I mean, you can have also results which are not 180, of course, and obtaining precisely 180 is actually impossible. So let's try to see how this depends on the sample size. Let's increase the sample size and take 30 and see that this distribution concentrates much more around 180. See, now it's a little bit more concentrated, and if we take 100 here, it should be really, really, all the mass will be concentrated around 180. So yes, nearly all the mass, I mean, and that's why I fixed the endpoints, because otherwise the programmer automatically rescales the axis, and you will not see this concentration phenomenon. So uh, changing, increasing, so we can see, have an idea, we can have an idea of the distribution of the quantity, of the random quantity, which is the sample mean, by looking at the above plot. So the law of large numbers tells us that this will be a delta around 180, so only concentrated around 180. So as n increases, the distribution concentrates more and more around mu. And this is was the law of large numbers. So the central limit theorem told us it was more complicated, and was about like the error you make when you approximate the 180 with the real mean, with the sample mean. So basically, the law of large numbers was this one, that this mean is equal to the real mean plus some error, which is a random quantity, which is defined as the difference of the sample mean and the real mean. And the error, the central limit theorem further specifies this error, tells us that the error is equal to, it has to be small, and it is a square root, small as a square root of 1 over square root of n. Then there is here a sigma and a standard Gaussian distribution, so plus another error. So sigma is the mean, is the standard deviation of x, of the population x, or of the random variable x, is the same. And Z is a standard normal distribution. Um, so to verify this theorem, we can simply plot Z. So simply we take we can isolate Z. So Z has to be equal to this error square root of n divided by sigma times the error. So this another error, sorry, has to be smaller than 1 over square root of n. So let's use this notation here. So this is another error times 1 over square root of n. So it has to be smaller than z, this second term. So let's write it in this way. So z has to be equal to square root of n. Isolating z, we obtain that z has to be equal to square root of n times the error divided by sigma plus another error, let's say. And so let's neglect the last error and recall that the error was the error you make when you approximate the real mean with the sample mean. So z has to be equal to square root of n divided by sigma times the difference between the sample mean minus the real mean. So to verify the central limit theorem, let's try to plot this quantity here. So we simply take this. So the mean. Now the point is that we know the mean of. We can take mu equal to the mean of the population. So the heights and sigma as the standard deviation of the population. And now we need to plot the sample mean minus the real mean times square root of n. So n here is the sample size. So the sample size was about around 100. We have saved it. So let's take the same values. So sample size equal to sorry to 100. Then k, the number of times we simulate this z, number of times we simulate z. Let's take it as 1000. And finally, let's compute this z, which is the mean of the sample. So we sample from the heights 100 heights, and we compute the mean. Then we subtract the real mean, mu, and we multiply it by the square root of the sample size. And we divide everything by the sigma. and we save it into the vector many z, let's say. And let's copy and paste let's plot the histogram to see how it distributes. Okay, I have to fix the extrema. Now it's centered around zero, this quantity here. So between -5 and 5, let's say. Okay, did I? Ah, okay, of course, I didn't replicate. Okay, many z was only one z, so we have to replicate this procedure k times because I did. Okay, I didn't do it. So now you should see the distribution of this case, these z's, and this a Gaussian, a Gaussian. Now, first, before like plotting the density and see that this, as we did last time, it coincides with the standard normal. Let me say what are we doing. So what are we doing graphically? Graphically, if we take the sample mean, so we are plotting, we are centering the histogram of the many sample means, and we are zooming by a factor of square root of n. So what are we doing? We are going here. We are placing this 180. We like translate the whole graph in zero, and then we zoom in and see how by a factor square root of n, square root of the sample size, to see to make it more wide because it's concentrating, and so this is graphically the central limit theorem, even if I think it's best understood as like with this analytical expression. But graphically is this procedure, and let's simply plot the density to see that it coincides with the um, the density of a normal distribution. So let me do it. We already did this last time, but why not do it again? So let's plot on the y-axis the statistics, sorry, the density. Um, so and let me plot also the density of a normal in red, and see that basically uh, they overlap. So if one has a better computer than mine, I can also increase the number of use this code and see that this approximation is very, very precise when you increase the sample size, and you can see that it is very good for this kind of data. Then the more the population is spread, the more the worse is this approximation, and you need a bigger sample size. But this is the central limit theorem. So, and this is what we did last time, basically. So, do you have questions about this? The codes, the everything? Okay, no, if not, I go on. So, today I wanted to do the t-test. So the t-test is a test that is used for numerical variables. So and for so the binomial test was for categorical variables. So you could have only two values, zeros and one, which could be not numbers, could be like simply a categorical variable with two levels, like I don't know. Uh, we did the example of formal and informal variant used by in a linguistic experiment. In this time, the t-test is used for numerical variable. So, for instance, let's make the example. So, the heights of the citizens of Amsterdam uh, so so the mean height of the citizens of so the mean height of citizens of Amsterdam is like 180, let's say. We want to test so to test so we think that in Moscow people is less tall, so we think that the mean height in Moscow is lower. So let's take we can take samples. So we can take for instance we can have the first sample can be I don't know 178 179 and 177. So the question is, would okay, let's take also two more numbers, so 180 and again 179. So we measure the height of 5 people. So would this suffice to claim that in Moscow people are shorter? So the idea is that it is an int, but I mean it's not really too much data, so it is not really too much data. And so what I want to do now is to give you samples that give you a stronger hint that people in Moscow are shorter. So let's put some samples. So let me call this as some first sample, and let me give you some more samples. So first, let's take a sample, another sample, which is 176, 177, 175, 178, and 177. So, okay, then let me give you also a third sample, which is, let's say, uh, okay, the mean of this sample is 100, a little bit less than 179. So let me take a, a more a better number actually, so that I will not have to put commas. So let me take here, define this as 178, sorry, 177, so that now, okay, sorry, this was 170, okay. So let me call this 178, and this 177, so that now, let me compute the mean also. I don't want to have commas, so let me simply change it until I find something. So let me decrease this one by 3, so 100. Okay, now should be okay. So, and I will change this accordingly. So I subtracted, I subtract to every element 1. Okay, so then this other element will have the same mean of this one, but we will be a little bit more spread around the mean. So let me simply take 175, sorry, more concentrated, let's say more concentrated. So around 178. So let's take 175.5, 178, sorry, 178.5, 178, 179, and 177. And let me see if they have the same mean and if I didn't make any error. Okay, let's take here 170 and here 179.9.5. Okay, okay, well, it's under, should be quite clear. Okay, now, and the last sample instead will have a lot of numbers more. So it will be like 178, 179, 179, 179, 177, 180. Something like this. So why these samples? So these samples give you a stronger hint on HZ, so on the fact that people in Moscow are shorter. So these results give you a stronger hint that the above that the people in Moscow are shorter. Why? The question is why. So in the first case, well, the mean of the sample is smaller. So of course, it's a stronger hint that people in Moscow are shorter. So in the first case, the mean is smaller. Then in the second case, the mean is the same actually. So you see, it is not why evident why it gives you a better result, so a better int. Well, the reason is that the data is more concentrated around 175, which is the mean. So you may imagine that if you're going to sample more people, like since the data is not spread around 178, maybe it will be a little bit more likely that you will sample a height which is around 175 rather than obtaining a result which is bigger. So the second, if you agree, I don't know if you agree, that the second sample is better since since the standard deviation, the how much it spreads around the mean is smaller. So is better since it is less spread around the mean. And the last result is simply better because you have a lot of data. So I mean, if you take more data, well, the result is stronger because you may imagine that you have sampled a bigger fraction of the population. So, and the possible fluctuations due to randomness are considered more here. So, sorry, are well, if you take a bigger sample, the law of large numbers tell you that the mean, you approximate better the mean. So fluctuations go to zero when the sample size goes to infinity. So the third, in the third case, the result is better since the law of large, since the sample size is bigger. Now, there is a statistic which combines these three elements, which is called the t-statistic. So, so maybe I should recall what is the standard deviation. So let x1 xn be a vector. Then, okay, sorry, I will do, okay. Let x1 xn be a vector, and what is the standard deviation? Well, the standard deviation is simply, we take this vector, the components of the vector. So the first component, we subtract the sample mean, the mean of the vector, and we do, so this first component is like the difference between the first element and the mean of the whole vector, and it's like measures how far is from the mean. So we take all this quantity here, and we do the average of it. But if we take this quantity here, they have a sign. So it's like this sum would be zero, because by definition of mean. So we simply square them to take some positive numbers out of them, to make positive numbers, and we take also the mean. Actually, we don't take the mean, we take the mean, we divide by n minus 1, because of some statistical reason which are not important for what I'm going to say, but you can think that it is n instead of n minus 1. And then to obtain the same units of measure, we take the square root, because we would like to have the same units of measure. So this is the standard deviation of the vector. So there is a statistic which includes all these three facts. So the second fact can be rephrased by the fact that the standard deviation of this second sample, sample 3, sorry, is smaller than the standard deviation of the first sample. So is bigger, is smaller. So there is a statistic which includes all these three elements, and it is the t-statistic. So let's fix a guess for the mean. Sorry. Let's fix a guess for the mean, mu, and let's call it mu guess. And let's no, not mu guess, because this is the null hypothesis. So let's call it mu zero. And it's not a guess, but it's simply let's fix. Let's assume that the mean of the height in Moscow is a certain number, mu zero, which in this case is equal to 180, which is the mean of the heights of people in Amsterdam. And the t-statistic is simply so. And let's take also sample size. Let's take a sample of size n from the citizen of Moscow. Heights of citizens in Moscow. And we compute the t-statistic, which is simply the square root of n times the difference between the sample mean minus the real mean, sorry, the hypothetical mean, the thing that we want to disprove. So we want to say that the real mean is smaller than this mu zero, divided by the standard deviation of the vector, the standard deviation of the vector x. So this expression contains all the above ingredients, so the sample size, the standard deviation, and the difference between the sample mean and the hypothetical mean. So in the first case, in these cases, so if it is true that people in Moscow are shorter, how much this quantity you expect it to be positive, negative? So if it is true that the mean of the heights in Moscow is smaller than those in Amsterdam, what kind of t-statistic you expect? Do you expect to see? Well, you expect that the sample mean is smaller than mu zero, so you expect to see negative quantities. So and so if the sample size, if the sample has one a lower mean, as in the first case, a smaller variance, a smaller standard deviation, as in the second case, and or a bigger sample size, as in the third case, the hint in favor of saying that the population in Moscow are shorter is bigger. So the hint in favor of saying that the mean height in Moscow is smaller is stronger. Uh, it corresponds to a smaller t-statistic. Okay? So let me repeat if you have any questions, let me repeat it. So we made, let me summarize. So we know the mean height of citizens in Amsterdam, and we want to test whether this mean is lower in Moscow because, well, people in Amsterdam is very tall, so probably it's true. So we don't know, we don't have money to measure all the citizens in Moscow, so we take a sample. Now, what did I do? I gave you some examples of samples, and all which confirm the hypothesis. But the first one is not really strong, and so I gave you some stronger samples. Each one of them is stronger for a reason. The first one is because the mean is lower. The second one because it is more concentrated around the sample mean, and the third one because it's a bigger sample. And all this information is summarized in this t-statistic. So this is we have all the ingredients to perform a test. What are these ingredients? Well, a null hypothesis, which is that everything behaves as uh, as it does in Amsterdam. So we are sampling from a population of height of mean 180. Then we have an alternative hypothesis, which is we are sampling uh, from a population of mean mu smaller than 180. And let me denote like the mean of the null hypothesis as mu0, simply because it will change later when we do some different examples. And so that the alternative hypothesis is that mu is smaller than mu0. And we have a statistic, which is this t, which depends, of course, on the sample. Uh, which behaves in two different ways. Is a statistic behaves in two different ways in two different ways whether if h0 or h1 holds hold. So in the first case, in the second case, sorry, it tends to be smaller. So what in what does this t-test consist? Well, if this t is smaller than a certain t-critical, the decision rule we reject H0 in favor of H1. Otherwise, we do not have enough information. So, and this is the test, and we simply need to define this t-critical. So, and this is done every time in the same way. So, as with the binomial test, this t-critical, how to fix this t-critical? So the test is defined once we fix the t-critical. So do you, so are you, so are you following like at least what is the decision rule? So, and why this t-statistic is smaller if H1 is true, rather because, well, if H1 is true, since the sample mean, which is random, is an estimation of the real mean. If the hypothesis 1 is true, it means that this sample mean is smaller than mu0. So you can obtain, of course, positive values because maybe you are sampling from the 10, from the all the highest people in Moscow, which would be, and in that case, will be much bigger, but it is a very unlikely event. So this tends to be usually when you take a sample, you take the mean, this approximates the sample mean, so this is small. Then if this is less or equal than 0, then if n is big, it will be even smaller. The more n is big, the bigger the n, the smaller this number. And if the standard deviation is small, since it is a denominator, this will be a number which is much bigger in size, but since it's a negative number, much bigger in size means that it is much smaller. So we can actually try. So let us implement it. So let's try to see actually this statistic. So let me first define a function, t-stat, which simply computes the t-statistic from a sample. So we take a sample x and a guess for the mean. So let's say mu0. And we compute the t-statistic. So it is the square root of the length of the sample, so the sample size, which is x, the sample, and multiplied by the difference between the sample mean, which is the mean of x, minus the real mean, which is mu, so not the real mean, the mean in hypothesis, in the null hypothesis. Then we have to divide by the sampled standard deviation. And this is the t-statistic exactly as we have defined here. And let's compute it, let's say so in this case, the real mean, so let's compute this t-statistic, yes, in case, so mu0 is in this case is the hypothesized mean, which is the mean of the height of the population in Amsterdam, which is 180. And let's put the first sample, then also the second one and the third one, the fourth one. and see that is smaller in the last three cases. So let's see. Sample 4, why it is, has not been found. Okay. Okay, well, actually, it is smaller in sample 1 than in sample 4. So let's add some more numbers like 179, 179, 179.5, and now it should be smaller. Yes. So for these three reasons, the last three the statistics are smaller, but still one is an hint that H1 is true. So do you have questions of what I'm computing here? Like I have defined this quantity, which is a statistic, I mean a function of the sample. The only thing I can compute for real, because I do not have access to the population. I can only take samples, and I can compute functions of this sample. And this, if H1 is true, as in this case, if H1 is true, we do not know if it is true or not. We can take a sample and see this t-statistic. If it is small, well, it is more likely that H1 is true than H0. So maybe let's compute the distribution of this t-statistic, just to see in two cases. One where H0 is true, and the other one when H1 is not true. So let's see the distribution of this statistic. When H0 is true and when H1 is true. So in the first case, let's take, I don't know, let's take an exponential random variable. So let's take a sample size, samples of, say, 10 numbers, and let's compute the t-statistic of a sample taken from a non-exponential distribution. So this stat. So in this case, mu is equal mu0. Mu0 is 1. So the real mean of the mean of an exponential. And let's compute this, the mean, the t-statistic computed on the sample. So t-stat of the exponential sample of size 10. With mu0, which is the real mean of the exponential. So here, the hypothesis, here H0 is true. H0 is true since the sample is taken from a distribution of mean mu equal to mu0. And let's compute the t-statistic. So, because we obtain some numbers. to compute its distribution, we use the law of large numbers, and we replicate this procedure k times. So we take many of these t. So we fix k, which is, say, 1,000, 10,000, let's say, and we replicate this procedure k times, and we save this vector into many t's, and then we plot it. Maybe I have it, no, I have it saved, so I don't need to rewrite everything here when I was reviewing the central limit theorem. Now, many t's, and I plot density. Mm, so let me see. Let us. So now we can try to see this distribution if h0 is true. Well, it is centered around 0, but you can see some. It is not so unlikely to see. mm, so it's not really too much centered. You can see numbers between -3 and 3, quite no, -3 and 2. I would say quite often, but and this is the t-statistic. So we can, if we increase the sample size, let's see what happens. This t-statistic it becomes more like a normal. But okay, so this is the kind of picture you have in mind if H0 is true. What happens if you're testing if actually H1 is true? What do you think it will happen? So these points will be much more on the left. So let's try to test an hypothesis which is false. So we take now our mean, our hypothesis of the mean is like 2, so that now mu is smaller than mu0. So H0 is false. This is the mean of the mean given mu0 is the mean given by the null hypothesis. So like that people in Moscow are as tall as people in Amsterdam, which I don't know, probably is false, but mm, so probably it is smaller. So H0 is false since the sample is taken from a distribution of mean mu equal to 1, which is smaller than mu0 equal to 2. And you expect to see everything on the left. So let's try to see it. So you see it's centered around 10, -10. And if we increase the sample, so I mean, here if we obtain a value of -5, sorry, of -5, I mean, or -10, it is almost sure that it comes from this distribution here, because here you see, you don't see, basically you don't see even -5. I mean, it would be really, really unlikely. So the question of testing, so if you assume that we observe t equal to -2, let me put it with a vertical line. So the question is whether this minus 2 comes from this distribution or the other one. Of course, it can come from this distribution, and as well it can come from this distribution. Okay, well, in this case, in this case, of course, it cannot come from this distribution, but it could come from another. I mean, the hypothesis, this is only a model in the hypothesis H1. The hypothesis H1 is that there is a mu zero, so there is a mu which is smaller than 2. In this case, I'm putting mu equal to 1, but let's say that I take a random variable of mu equal to 1.9, 1.8. So let's say an exponential of a smaller parameter. So an exponential of parameter 2, sorry, of parameter 0.5, that is 0.4. Okay, now in this case, parameter 0.6, let's say, so that the mean is more near to the to 2. So now in this case, I mean, it is more likely that this t equal to minus 2 comes from this distribution. So this is almost the mean. So the question is the following. Does it come from the first or the second one, or the second histogram? So, of course, a statistic, so it can come from both. So if you really, if this model is completely, you're sure that it's false, it comes from sure for the first one, but you are testing like two plausible hypotheses, so that let's assume you think that you are really undecided from which two histograms. If you observe this data, you have an hint that this is maybe, it comes maybe from this one. So, and the decision rule is the one that I told you. And now we have to fix this T critical. So how to fix? And this is the question that defines the test. Maybe I will answer, no, I don't know. Do you want to take a break and then reply, then continue with this testing test, or you want to? Okay, no, let me do a let me fix the T critical in a certain particular case. So how this T critical is decided? For every test, this is the same. So we fix a type 1 error probability. So this is the way we want to control it. So we have to fix something to fix the test, and we fix this error probability to alpha. The type 1 error probability provided H0 holds. So if H0 holds, we want to be wrong only in a fixed amount of cases. So let's say we fix the probability that T is smaller than certain t-critical, given that h0 is true, equal to alpha, which is usually equal to 0.05. So why this choice? Well, because on here we have that the probability, this is on the left-hand side, this is the probability to react H0 given H0 is true. So it's the probability that, so it's the probability that if we are actually, if H0 is true, that we are making a mistake. So we fix it, and this automatically will fix our t-critical simply by inverting this function. You see, we have here t-critical, this on the left. On the right-hand side, you have alpha. On the left-hand side, you have a function of t-critical. You invert this function, you find the t-critical in terms of alpha. So now the question is how to invert the function, how to invert, how to what is on the left side, how to write. So this is the crucial question. This is what distribution we assume that t follows provided h0 holds. So this is the question we have to answer to define this t critical in terms of alpha. Well, there is a case which is if we assume. So let me so the first test we can define is the Z test, which is defined assuming that T distributes as a standard normal distribution, provided H0 holds. So why this is true? In which cases this is a good assumption? So this is the question, the first question. Then how to write T critical in this case. So these are the two questions that I want to answer. Well, let me answer to the second one. So a little bit of practice is always good. And then on the first part of the next hour, I will answer to the first one and then define the more used t-test, which is better. So how to find the critical in this case? Well, simply let's, so we have to compute. How does the t-statistic distributes? Well, as a normal, we are assuming. So t distributes as a standard normal provided H0 holds. by definition of z-test. So we see, let me plot the distribution. Um, between -5 and 5, I plot, I put the endpoints of this distribution. Well, okay. So I want to find the t-critical. So let's fix a t-critical. Let's guess it to be -1. And so let me define it before the plot of the graph. And let me add a vertical line at the critical. So I want to compute how is this the critical to be found. So this T critical is defined by this relation here. So I want the mass, the probability of finding a smaller t to be equal to 0.05. So here we are plotting the density. So the probability is the area below the curve. So I find t critical by imposing, since we are plotting the density, that the area below on the below the curve and on the left of the vertical line is 0.05 or alpha better. Well, there is a command which is really so it is the command is, let's say, alpha is equal to 0.05 and the t critical is simply found by taking the quantile function, so q norm, associated to alpha. This gives you this vertical line, gives you where this vertical line has to be placed to have on the left only alpha% of the area. So let me see which t-critical gives us. It gives us a t-critical of, okay, let me plot it. It's better to plot it. Okay, so the t-critical is here. And let me also plot it on the screen. So this t-critical is minus 1.64. Now, and is here. So now the test is defined. Simply the test, we simply collect the data, look at the t-statistic, and say if it is bigger or smaller than this 1.64. So I don't know if you ever looked at some old statistics book. So they had this, like half of the book were tables where you can find like this function here, this q binom, sorry, q norm. So they basically, for many different alphas, they had these values. And you to find now we are much more lucky. We have these computers that we simply need to type, and in less than 1 second, it will give us the result. In the past, a lot of people spent a lot of time computing these quantile functions. So the reason where that are used in this kind of ways. So now in the next part of the lecture, I will say which assumptions under which assumption this is this the test is a good test, and define the t critical for the t test, which is a little bit more on the right than the one of the. So I don't know if you have any questions. I'm here, but let's take a 15 minutes break. So see you later. So we left. We finished the previous lecture by defining this T critical for the test using this quantile function of the normal distribution. So the Z test, first of all, yes, the T critical is defined once we assume that that t, which is a t that depends on the sample size, on the sample, and on the mean, which is in the hypothesis zero, follows. So is defined once we assume a determined distribution. So we need to fix this distribution. So for the Z test, assumes that T distributes as a normal Gaussian. The t-test assumes that t distributes as a t-student distribution. So this is like a spoiler for the t-test, but the t-critical will be computed for the t-test simply by using the quantile function of the t-student distribution. So instead of typing qnorm, you type qt of the degree of degrees of freedom. Sorry, the t distributes as a t-student distribution with you have to this distribution has some parameters, so we have to fix them with degrees of freedom. This parameter is called the degrees of freedom equal to n minus 1. So, for instance, if the sample size is 100 is 10, the quantile function of the t distribution with 10 degrees of freedom associated to alpha equal to 0.05 will give us the t critical in this case. which is minus 81. So it is on the left of the one for the z-test. So for instance, the critical for the binomial test was computed. Okay, the hypothesis was greater or equal than a certain number, but if you would compute critical, the critical for the binomial test using Q binomial. This was an anticipation. So you see all the tests are work in the same way. You only need what changes is the statistic and the distribution of the statistic. In this case, the difference between the z-test and the t-test is not on the statistic, which is the same, but on the distribution we assume on the statistic. So why it is a good hypothesis, the one in which cases it is good to assume that the t-statistic behaves as a normal? Well, it's a consequence of the central limit theorem, why, and of the law of large numbers. Why? Because the standard deviation, the sample standard deviation, so let's call it SD that depends on n, which we have defined before, is like the sum, the mean of xi minus the mean, the sample mean. To the power of 2, and we have to take the mean of this quantity here. So x1, and we have to copy and paste it n times. So I'm changing the one with the respective number, so until n. And we have to divide by n minus 1, or n is the same. For what I'm going to say, this is the standard deviation of this sample. Sorry, this is not the standard deviation. I have to take the square root. So this is the standard deviation. Well, for in view of the law of large numbers, now this is a good estimation by virtue of the law of large numbers. You see, I'm taking the mean of some quantity, and then I take the square root, but inside the square root there is a mean, and this mean converges to the mean of, I mean, it can be proved. I don't want to do it because it's not technical, it's even, but let me just say that this is a good approximation, is a good approximation of the standard deviation of sigma, the standard deviation of the random variable xi, sorry, of x. So I'm taking a sample, independent sample. So if this vector of x1, etc., etc., is an independent sample, is a sample of independent and identically distributed random variables. Example, I'm sampling from the population of Moscow, the heights, these are independent samples, and they are all identically distributed because it's like extracting balls from an urn. So which the number of each extraction has the same probability of extracting a determined ball. So um, if this is true, these samples are from a distribution, uh, so are identically distributed random variables that distribute as x, let's say, then and sigma is the standard deviation of this variable x, then this standard deviation, this sample standard deviation is a good approximation of the real standard deviation of this sigma that we do not know. We can compute this sample standard deviation, but we do not know the sigma as for the mean. So let's use it in the definition of the t-statistic. In this case, the t-statistic, which is the square root of n times the mean, the sample mean, minus the mean, the real mean of the of this x. So h0 is true. Since h0 is true, this mu is, I'm assuming it, that h0, that the mu is the real mean. So mu0 is equal to mu. And we divide by sigma, so not by sigma, by the sample standard deviation. This is the t-statistic that we introduced before. But in view of the law of large numbers, this is similar to the square root of n times the difference between the mean and the sample mean and the real mean. And we divide by sigma, since the standard deviation is a good approximation of sigma. This is the quantity that more or less similar to t. Well, this, let's go up where we reviewed the law of large numbers, which was here. This is actually exactly this z. So when n is large, precisely the law of the central limit theorem tells us that this quantity here behaves as a standard normal distribution. So the statement of the central limit theorem tells us is precisely the statement. So nothing more and nothing less, that if n is large enough, the above quantity distributes as a standard normal. Now, this is just an approximation when n is big enough. And a normal has very, very, very flat tails, so they decrease exponentially. It's very difficult to find extremal events. So, in particular, what does this implies on the t-critical? Well, implies that the area on the left is small in the tails. So it will give a t critical, which is a little bit more on the right. So you need it is easier to so it has flat tails, the normal distribution. So let us compare instead. So this is the reason why we assume it can make sense to assume to use the t-test, so the z-test. The t-test assumes another distribution, which is the t-student of n minus 1 degrees of freedom. So let us see graphically these two distributions. So I plot the standard normal in black and in red the t-student distribution, so the density of the t-student distribution, and I need to pass other arguments, which is only one actually. It is the number of degrees of freedom, let's take it to be 4, to better see the difference between t-distribution and the normal distribution. So I color it in red, I said. So, okay, and I fix a better interval for the x-axis, so x-lim, let's say between -4 and. So let's see the result. Well, you see that the red one, which is the density of the t-student distribution, has tails which are fatter. You can have more mass. You have more mass on the extremal events. You give more. So t is assumed that can be larger with greater probability. So let's see also the one with 2 degrees of freedom, where this is even emphasized. So I would say yes. So, but as the degrees of freedom increase, this t student distribution becomes a normal. So, like I would say that for 100 degrees of freedom, you will see no difference. Yes, exactly. So, but until 8, you can see that. I mean, 8, I guess it's also very similar, but you see there are some fatter tails in the red distribution. So now, why it makes sense to assume that uh, T behaves as a t-student distribution? So the reason is because of this lemma. So let me write it. So lemma, let x1 xn be independent samples, independent and identically distributed samples from a random variable x, a Gaussian random variable. Of mean mu, say of some mean and some standard deviation. Then the fact is that the t-statistic computed using these Gaussian samples distributes, so you and with mean, the real mean, let's say, okay, a Gaussian non-variable of mean mu. And this t-statistic distributes as a t-student distribution of n-1 degrees of freedom. How to check it? Well, we can simply plot many times the t-statistic, so let's do it. Why not? So let's take a sample size, let's say of 4, so 5, so that we can see better the difference between the t-student distribution and the Gaussian distribution, and we compute the t-statistic of, let's take mu equal to 0, and let's take the normal distribution, the t-statistic computed using a normal sample of 5 elements. So we can see what this, okay, we can do this many times, we obtain different results. To plot the distribution, we need to replicate this procedure many times. So let's take k equal to 10,000 and replicate this procedure k times. Many t's will be equal to this procedure. We collect all the results that I obtained when replicated this part, and okay, I will take and I will plot the histogram. So I have saved this um, okay, this the plot of the histogram. I did it 100 of times this lecture, so I simply copy and paste it, and I also see that I called many t's in also here, so I don't need to change names of the variable. And let me plot the density, yes, and also I add the t-student density to the plot. dt, I have to pass the 4 degrees of freedom also, args equal list degrees of freedom equal to 4. So let me see if they coincide, they correspond. Okay, they actually correspond, but let me be more, take some more beans. So and bigger k, so that will be better approximation. But maybe I expect too much from my computer. So okay, no, it's good. I don't know why it is. It is not very pretty much centered, this plot. Maybe let me put some endpoints. So between -5 and 5, and let's see, is a good approximation. you see it is very, very good. And the normal is let me plot also the normal function. The is not a good is not as good as this one because it is a true result. So I'm plotting. They are distributed exactly as a t-student distribution. So let me do it again. So you see, the normal distribution is really not. I mean, it's not really not good. Is not the true one. But as the degrees of freedom increase, the degrees of freedom must be equal to the sample size minus one. So maybe let me decrease k and increase the sample size to 15, and this will be much. They will look really pretty much as a normal. So in the particular case, I am sampling from a Gaussian distribution population. Then the t-test, the t-statistic distributes exactly as a t-student distribution. Of degrees of freedom and sample size minus one. So the assumption of the t-test is that the vector, the samples, and the population from which I'm sampling is not far away from a Gaussian, which is quite hand waving, but there are some measures to see how much Gaussian is your data. So if it is not Gaussian, this test is not really exact. But if it is not so, I mean, being Gaussian means not having too much extremal data. So the assumption is that you don't have too much external data. So it's not away from a Gaussian. So, and now let's do some practice. So do you have questions concerning this? So let me simply perform this step. Recall the definition also of p-value because it's always important. So, okay, no, maybe it's better to recall it later, but it's super important. Uh, yes, let's try to perform a test. So the first test we can do is let's take a population. I had saved the population like some age, like the age of the population of Moscow, of Amsterdam actually, because the mean was 180. So these are the age of Amsterdam population, of the Amsterdam population. So let's test a true hypothesis. So H0 is that, so let's take the mean of heights, and let's call it mu0. So this is the real mean. Mu0 is the real mean, and let's test the hypothesis H0, that is mu is equal to mu0, and the alternative hypothesis that mu is, let's say, smaller, because we believe that maybe it is smaller. So in this case, H0 is. So let's perform a t-test. We take a sample of 10 people, let's say. Um, let's take the quantile function of the t distribution. Let's take alpha equal to 0.05. We take the quantile function and the number of degrees of freedom equal to sample size -1 to see what is the t critical. This is the t critical. Then we plot the observed t, so t of the we sample from the vector heights we sample with a sample of 10 10 eighths, and we compute the t-statistic, and we assume that here we put mu0, which is the real mean. So this is H0 is true, and let's also perform the test using the R command t-test. So we have to pass this sample. So let me put this sample, define it before the function t, and save it into sample, no, into sample dates. So we take this sample, we ask people how tall are you, and then we compute using their replies this sample, this t-statistic. And we do the same using the command t-test of R. So we have to pass also the mean, and we need to put which alternative we want. So here the alternative hypothesis is that the mean is lower. So this should give us the same results. Let's see what mu0 t start, sorry. two-sided less, so not lower. And let me also compute the t-critical. So let's see. Yes, okay. So on the first line, we have the t-critical, which is minus 1.83. The second line, the observed statistic, which is 0.31, not even negative. So it's on the right, and we do not reject H0 in favor of H1. And indeed, we do the right thing because H0 is true. Well, we go here and see what kind of outputs the t-test function gives us. Well, there is the t-statistic, which is the same as we computed. So we know that it is the degrees of freedom, which are simply the sample size minus one, and the p-value of this 0.31. So what is the p-value? We have to remember it because most of the time the test in the papers you see the p-value, which is basically nothing deep, but is the probability of observing a number which is smaller than 0.31, provided that the null hypothesis holds. So that's important. But we will recall it later. So let me first finish the output of this command. So here it tells you the statement that is the true mean is less than 0. The alternative hypothesis is this statement here, so that the true mean is less than 180.00.19, and since the p-value is greater than 0.05, or the t that we observe is greater than the t-critical, we do not reject H0 because we need really an extremal value of t. So we would need like -2, -3 to reject H0. Instead, here is even positive. So no, we do not reject it, and it gives us also a confidence interval, which I did not explain what is, and the mean of our sample. So to perform a t-test is very easy. It's very easy in R. You simply need to type. So what is the p-value? The p-value is it's always as usual. For every test, the p-value is defined in the same way. So the p-value is the probability of observing a more extremal statistic, and this has to be put in capital letters, provided H0 holds. So it didn't work, this emphasizing this part, but I don't know why actually. Text, maybe let's call it text BF, no? Nothing. Well, text bold, text text it. No. Well, provided H0 holds. So, what changes in every test? The notion, the notion of extremal depends on the alternative. So, for instance, if the alternative was to observe that the mean is greater, extremal means greater, because the statistic tends to be greater if H1. So, depends on the alternative hypothesis. Then what changes also in every test is that the statistic, of course, how the statistic distributes provided H0 holds. These are the two ingredients that you need to compute the p-value and to perform a test in general. So in this case, the p-value would be the probability that the p-value of t is that t is so the p-value of t observed is simply the probability that our t-statistic, let me also denote its dependency from the sample, is smaller than this t observed, to observe a more extremal event. And in this case, extremal means smaller. This is the p-value, is the definition of the p-value of t observed. Ah, okay, no, I'm wrong, provided H0 holds. This is important. All the tests are performed assuming you are in H0. So it's like kind of what makes things computable, because in H0 you know the statistic of t, but not the thing that you would really like, because you would like to know the probability of H0 to be true or false, but in this you can only you compute everything while you are in H0, so you really don't know. But okay, let me see how to compute this p-value. Well, the p-value of, in this case, we observed 0.31, which gave us the p-value of 0.62. So let me copy this t-statistic and compute the p-value of this t observed and see that it coincides with the one that R gives us. So t obs 0.31, we compute the quantile function is the area on the left of the observed t, so the quantile function of the t distribution. We pass the observed t, and we pass the number of degrees of freedom, which is 10 minus 1, 9. And we see that the p-value is minus, no. So what's wrong with this? Maybe it's simply don't know. No. Well, this is the quantile function. Ah, no, I'm sorry. It's not the quantile function. The quantile function is the point where on the left there is 0.31% of the area. It is the cumulative distribution. So I have to write p, the probability function of t. Uh, this gives me the probability that t is smaller than t observed by definition, given h0. So, okay, probably I can also put here back this number and see that this 0.62 is precisely the p-value. So we know how to compute p-values, of course, and that's important. So we know how to do this test. So, for instance, let's now perform this test with a false h0. The false h0, let's say, mm, so let's take heights, which are the heights people in Amsterdam. We subtract 0.5 and we call it heights, I don't know, of people in Madrid. And okay, we know that now we take the t-test, we sample from people in Madrid, 10 persons, 10 people, and we perform the t-test. So we called sampled heights now we assume we don't know that we subtracted 0.5 to the vector of people, to the heights of the people from Amsterdam. So mu0 is again the null hypothesis, which is that the mean is the mean of from the people in Amsterdam. So the null hypothesis is that mu is equal to mu0, which is false in this case. The alternative, the alternative hypothesis is that the mean of this case of Madrid is uh, smaller, which is true. Which is true. And now we are testing the test. We would like that the test reject this null hypothesis in favor of H1. So we would like to have a correct test. Let's see if this happens. So I pass the sample dates. I pass the hypothesized mean, so mu0, and the alternative is that people in Madrid are less tall in mean. Let's see. Okay.
Okay.
What? Sorry. I heard some noise, but in any case, what am I doing here wrong? Because the p-value is 0.95, so that it is it is highly, so it didn't reject us, this hypothesis. So I'm doing something wrong, or simply due to randomness. So let me do it many times. No, 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 no. This is not. So why is this happening? Okay, so there is some mistake that I cannot spot it right now. That I cannot spot right now. So the mean of the vector heights, it will be 180. Let's see. Yes, is this one. The alternative hypothesis is that the mean is smaller, which I guess is true because I'm taking the heights of Madrid, I'm subtracting from the heights of before 0.5. Then I take a sample from the heights of Madrid of some sample size, and I'm passing this vector, yes, there. 0 here is this one, yes, and the alternative is that, yes. So maybe let me try to increase the sample size, but or to see what is the vector. Hmm. I cannot spot it actually. Probably take a sample size to equal to 1000, so there will be no randomness basically involved. So if okay, no, it was due to randomness, so it was a sample size which was too small. So you see now the p-value is almost is very very small. But if I had I chosen, as I did before, a small sample size, most of the time I cannot reject the null hypothesis. Um, so that's a good actually exercise because I don't know. I guess that if I take 50, it will be sufficient to reject it most of the time. No. Mm, okay, no, I had to deal with this because it is what it is. So now it has to be at least of the order of magnitude of 100. That's nice to know. So yes, in these cases, I'm rejecting most of the time the test, so I'm doing the right decision, but the sample size is quite big. Um, so this is, of course, the smallest is this effect, this minus. Here I should take the bigger the sample size I should take. So if here I put 0.01, I should take a sample size of 50,000. So to see something, I guess. I'm not even that. But if here I take 5, which is to say that the hypothesis 0 is not only not true, not true to a high extent. So in this case, a sample size of 10 people is perfectly fine. So I mean, so I hope that I mean you need to download so you need to play a little bit with these commands to simply get acquainted with some the order of magnitude. This is something that one can only earn with experience. But I hope it is clear the definition, the idea of this test. If not, please, I mean, I can answer, you can send me an email, whatever. In any case, I will correct the exercise, which were about the binomial test, and if you made them correctly, you basically know how to do every test. I will give you for the next week some exercises about the t-test, and nothing. Let me only finish remembering that what one wants to know is this quantity here. Uh, the probability that of H0 given that H0 is rejected by the test. So what is the probability of H0 given that you reject it, your text rejected, or I mean, it would be sufficient for at least better to know the odds, better than only knowing the p-value. So the odds of H0 after we reject it. So this would be like what I mean, it would be the ideal to know this. So the probability of H0 divided by the probability of H1, given that we reject H0. But to know this, you need to know like a lot of stuff. But it is very difficult to know all these quantities since you have to know, well, using Bayes' formula, what do we get? We take this quantity here. This quantity here is equal to this the same quantity, but the same quantity without knowing that H0 is rejected times the probability that H0 is rejected given H0, so H1 this is like a way of seeing the Bayes formula. So here X is simply a product. So better remove it. So you need to know the priors, which the prior odds, which is the probability of H0 divided by the probability of H1. So how much more you believe in H0 than in H1. And you need to, okay, you know that this denominator is equal to alpha. but you need also to know, sorry, the numerator is equal to alpha, but and the numerator, you need to know this quantity here, which is not really, you need to have an idea of this quantity here. So, of this quantity here. But this, for knowing this, you need, there are two issues. The first one is that you need to specify better what is H1 and to compute, to know, to estimate the distribution of the t-statistic given H1. I gave you some links about some real example, and you see that this is very difficult in general. So the test rather works uh, only assuming that H0, so it's like a proof by contradiction, but it doesn't tell you anything about H1. It tells you that only what you see is a rare event if H0 were true, and it's more probable that you see it under H1. So that's it. That's what I wanted to say for today. So see you. Have a nice weekend. If you have questions, just ask.